Okay, welcome to the second lecture of chapter 2, so part 2. So previously we spoke about the composition of cells, so basically the static view, and we ended with this dynamic perspective. And now we're going to quickly look at a very basic feature of cells, growth and metabolism, to give you a feeling of what cells do. Okay, so what cells... One feature of cells is that they can self-fabricate. Right, and that is what we associate with a system being alive. So that means that if we have a cell that after some time it has, say, doubled in size, and then it splits in two, and then this repeats. Okay? Now the time for this entire process, so this is birth to division. So this entire time is called, for instance, the cell cycle time or the generation time. And this time depends, of course, on the external environment. Okay. And so the nutrients and the toxins and maybe the temperature. Because clearly, in this first phase of growth, that is only possible if the cell can take up nutrients and convert those into cellular building blocks. Only then growth is possible. And that therefore depends on the external environment. If the cell can do this fast, so if it can grow fast, then this time is short, and then the generation time is short too. Okay, so fast growth means short generation time, right? Okay. So let's say we start with, we have a surface, okay? And the surface contains nutrients, and we place one cell in the middle. Then over time it will grow and gets a daughter. They will both grow. We get more and more cells. Okay. So we go from one cell to two. They each split, then you get 4. They all split, and then you get 16, etc. Okay, you go from 2 to the power 0 to 2 to the power 1 to 2 to the power 2 to 2 to the power 3, so 8, to 2 to the power 4, etc. 16. So it's 2 times 2 times 2 times 2 times 2. Okay? So after one generation time, you have 2 cells. After 2 generation times, you get 4 cells. After 3 generation times, you get 8 cells, etc. Okay? So, if we have a time axis like this, and a number of cells axis here, and I start with 1 cell, and then 2 is important, the value 2 is important, the value 4 is important, the value 8 is important, 16, 32, etc. 2, 4, 8, 16, 32, etc. Now I can think of this time axis as composed of pieces that are each 1 generation time long. Okay, so let's denote this generation time by tau g. This is one tau g, the other tau g, the third, the fourth, sixth, etc. And we know that after 1 tau g, I'm here. After 2 tau g, I have 2 cells, etc. etc. So, the dynamics goes up and up and up and up. So the dynamics is a rising dynamics, so we get more cells over time, and it's sort of, there's a speed up in there, right? So the slope of this line increases. So the increase is going to go faster and faster and faster and faster. And that is because each cell makes copies of themselves independently. So when you have 3 cells, independently they make copies of themselves. And that's more copies than when you would have 2 cells. So the exponential nature of it, so the exponential rise in terms of the number of cells, is due to the fact that they each independently do the same thing. So they repeat their cell fabrication process, each independently. So this is why it multiplies. Okay, so that also means that after 1 generation time, right, we have 2 times as many cells as we had on time 0. And after 2 generation times, we have 4 times as many cells. And after 3 generation times, we have 8 times as many cells when we start. So that means that the number of cells at time t is 2 to the power t, the actual time, divided by the generation time times the number of cells. Because if the time equals 1 generation time is 2 to the power 1, if the time equals 2 times the generation time is 2 to the power 2, if it equals 3 times the generation time is 2 to the power 3. So the rise in the number of cells with respect to time, if cells split, has to agree with this mathematical logic. Okay. And yeah, clearly this is exponential growth, right? Because there is 2 to the power, so this is the exponent, is associated with the rise in the number of cells. So the exponential nature of it is shown here. Now, if you remember your mathematics, if we would define the growth rate, so let's say we define the growth rate mu as ln2 divided by the generation time. If we would do that, then the generation time would be ln2 divided by the growth rate. If we assume that for now, if you substitute that, you get this. Just substitute that the generation time is ln2 divided by the growth rate, and this equals e to the power mu t if you apply your logarithm rules. Okay. So apparently we can convert 2 to the power something with base 2 to something with e to the power something. Okay. So we can have an exponent with base 2 and with the natural and with the constant e as base. Alright, and this is just a number. Okay, so the exponential growth. So exponential growth. Of cells that split in 2 can be described by 2 to the power t. Generation time and 0. This is based on logic. Thinking logically about what happens. And if you apply some matrix, you will see that this equals e to the power mu t times n0 when we define the growth rate as ln2 divided by tau g. Okay? So this is the thing, still the thing we have to explain in a moment why we did it like this. But let's think about this, okay? So this thing is basically the line that you see here. Yeah. Okay. And so now what we want to do, we want to figure out what the value of this slope is of this line. Okay, that is the first, that is now the next problem that we would like to do. So the slope of this line, right? Slope. Okay, that equals the derivative of this function with respect to time. Okay? So slope of nt versus t plot equals dn dt. Okay? So we need to take the derivative of this, of the right hand side and the left hand side, to figure out what the slope is. Well, it turns out that this is mu times e mu t times n0. So if you take the derivative of this thing with respect to time, then you find this. So this equals mu times nt. So the slope at time t equals the number of cells that we have at time t and this growth rate. Okay. So this also tells you that the slope is continuously rising because you get more cells that each grow at a growth rate mu, and that growth rate mu has a relationship with the generation time, and that is just the time that it takes for a cell to double itself and divide according to this fundamental process that applies to cells that split in equal halves. Okay, so what have we achieved? So we started from this really logical argument that if you have cells that split in equal halves, that they first have to grow, double in size, and then split, and then you have two of them, and each of them do this process again. So after one generation time you have two cells, then each does that by itself, so after two generation times you have four cells. After 3 generation times you have 8 cells. After 4 generation times you have 16 cells. So after 1 generation time you have twice as many as you started. After 2 generation times you have 4 as many as you started. And at 3 generation times the factor with which the number of cells has increased since the beginning is 8. So that means that this relationship needs to hold. The number of cells at time t is 2 to the power t divided by this generation time times the number of cells that you started. And if you then define the growth rate as this, such that the generation time equals that, then you get 2 to the power this, which equals e to the power mu t, which is a rule. It's a logarithm rule. So these two relationships both specify this curve. This curve has a slope. And this slope is the derivative of this function at this moment in time. That's what slopes are, you know that. So that means that if I take the derivative of that function, I can determine the slope. And if I do it on the right hand side, it turns out that the slope is going to be equal to mu times the number of cells at time t. So the slope at time t equals mu times the number of cells at time t. Okay. So that's the first relationship that is also derived in the syllabus. And there are some exercises associated with that. Now the next question is, so the next problem that we need to think about is, so what is growth? Okay. So how is it possible that cells actually grow? So let's have a look at that. Because there is something surprising going on. And the surprise is already a little bit in the words self-fabricate. So let's figure out in a moment, when I've cleaned the board, what that means. So the argument is that exponential growth so at a fixed growth rate mu, or equally well a fixed generation time. Okay, so the first thing is to figure out how do we get a fixed growth rate. Okay, so how do we do an experiment in which the generation time is fixed? So I already told you that the generation time is determined by the environment, and that is because growth, so the time that it takes to make a copy of a cell, the generation time, is determined by the quality of the nutrients. If you have good nutrients, cells grow fast. If you have poor nutrients, cells grow slow. If there are no nutrients, there is no growth, and then generation time clearly is infinite. So if you want to reach a fixed growth rate, then the environment needs to be constant. And then you can have self-fabrication, which means an exact copy is made. An exact copy is made. That means something really, really, really weird. So here we have a cell. Sometime later it has grown. So if this is the length of the cell time t, and this is the length of the cell at time t plus, say, delta t. So this is the part of the cell that grew in delta t time. This part of the cell is an exact copy of what already existed. So that means that in this part you find per volume the same number of molecules as in the old part. Okay, so same molecular composition as in the old part. So that means that, so when you have 10 molecules per microliter here, or sorry, 10 molecules per cell here, right, and I make half a cell, then 5 molecules appear in this other half, alright? Such that the total number of molecules per cell of each type of protein remains fixed. So that is what it means when you make an exact copy. So if you think about the Mars bar, right? I think we all know what those are. So here we have the Mars bar, and here there is this sugarish layer on top, this caramel layer on top. And here you have the chocolate piece underneath, surrounded by chocolate. So a growing Mars bar, so if it would be possible for a Mars bar to self-replicate, then it would make over time all these different elements in the same proportions. Okay, so you have the sugary part, the caramel part, and the chocolate layer on top. Okay? And that means that if I take a piece of the Mars bar, this is indistinguishable from another piece of the Mars bar. And that's the same inside this cell, except for the caps, the ends. But otherwise, all these pieces are the same. Okay? So it is as if there is a unit cell that you can distinguish. Okay, so this exponential growth means that each molecule that the cell consists of, and it consists of these molecules in certain proportions, so 10 times as much of this protein relative to the other protein, these relative proportions are being conserved in the new part of the cell that grew in a certain duration of time. And why is that? Well, we're living in a constant environment and this cell has a steady state, so a constant rate of cell fabrication, and it's trying to achieve an exact copy of itself. So that means that the cells that are being made are indistinguishable from the cells that were the ancestral cells. So that means that every concentration in the cell remains the same when the cell is growing. Okay, and that topic is called balanced growth, and that is explained in the last chapter, but I don't think we'll reach this last chapter next year, because I think that the teaching will be a little bit slower now in Corona times than it used to be, but that's fine. Okay, so all the same building blocks of cells need to be made in all the same relative proportions. Okay. If that happens, then the generation time, the growth rate remains fixed. Okay, so what needs to be made? Protein needs to be made. mRNA needs to be made. tRNA needs to be made. Ribosomal RNA needs to be made. DNA needs to be made. Lipid needs to be made. And then per gram cell we have a certain percentage protein, a certain percentage mRNA, a certain percentage tRNA, ribosomal RNA, DNA, and lipid. And this makes 1 gram cells. So what I just told you is that all these percentages are remaining the same when the generation time and the growth rate is fixed, and that can be achieved when you keep a constant environment, and then indeed you can observe that the number of cells equals exponentially with time with a constant exponent mu. And that occurs when all these relative proportions remains fixed. So if the caramel part, let's say, is 20% of its weight, and this is 75% of the Mars bar's weight, and the chocolate part, chocolate layer, would then be, say, 5%. So, yeah, 5%. Okay, so we're keeping these percentages fixed. So we're making the cell the growth resembles making a Mars bar that is indistinguishable from the Mars bar that you started with. Okay, so this is cellular growth, yeah, at a fixed growth rate at least. So now all these proteins consist of nitrogen, carbon, hydrogen, oxygen, sulfur. And mRNA, well, essentially all have the same exponent, and also phosphate. They have the same component, but maybe not all of them contain sulfur. So all these elements need to be made. So these need to be made from amino acids, right? So they have the right composition to make proteins. mRNA is from, we need nucleic acids for it. And we also need, we need deoxynucleic acid for DNA, and we need fatty acid metabolism. We need fatty acids to make lipids, and all of these are made by metabolism. And metabolism needs proteins. These proteins play a role in metabolism, and the input for metabolism is nutrients. So we need nutrients that consist of these elements. Because if one of these elements is missing, you cannot make a cell, and then growth rate will go to 0. So the environment partly determines the nutrients, or the nutrients are part of the environment. They are taken up by the cell. These things are being converted into precursors for growth. And in this case, polymers are made of amino acids leading to protein, and polymers are made of nucleic acids leading to RNA species and DNA. And then fatty acids need to be made that then form lipid membrane, the lipid membrane surrounding the cell. Okay? And in case we find growth at a fixed growth rate, so the number of cells increases exponentially with a fixed exponent, then what we know is that all these proportions that the cell consists of, these macromolecules, remains the same. So metabolism supplies the material for cell growth. Okay, so let's do one more thing. So what happens now if nutrients deplete? So let's look at the situation where we first start with a lot of nutrients, such that from the perspective of a single cell there is an infinite amount. So that means that when a single cell would consume some of those nutrients, the nutrient concentrations, they would hardly change. Okay? So let's mimic such an experiment. So we're going to take an Erlenmeyer, right, a flask, fill it with medium. So there is growth medium. And with that I mean nutrients. And we place a single cell in there, okay? Now it's going to make copies of itself, it's going to self-fabricate, it's going to grow, and until it has doubled it will divide. And that cell will then do the same thing. While the other one, the previous one, is still doing it, so they're all happily growing. And in the beginning, of course, if you would here have the nutrient concentrations, they would all, they would maybe go down a little bit, because they are being consumed after all. But that really doesn't affect the growth rate. So from the perspective of a single cell, it is still, there is an excess amount of nutrient, and they really don't miss that one of these or a few of these nutrients are being taken up by other cells. It really doesn't affect their own growth process. They can continue to grow at the same rate because nutrients are in excess. So in the beginning, the nutrients, they go down, but really slowly, right? Really slowly until they are depleted. So at some point, so let's say roughly here, so the nutrient depletion affects cells. But here we have nutrient excess. Okay. So when there is nutrient excess, it is as if the cells live in a constant environment where nutrients are not depleting. So that means there was exponential growth. But as soon as it kicks in, the growth rate becomes smaller and smaller and smaller and smaller until growth stops. So the number of cells with time, first in the excess period it's exponential. But here growth is limited. And something is limiting growth, so the growth rate is